Bismillahirrahmanirrahim. Let us begin our next session on category theory. In our previous session, we discussed the concept of product in a category. Today, we will discuss the concept of co-product in a category, and we will also discuss little bit about duality in a category. So, in this session, we will discuss concept of co-product. Before coming to this concept, let us recall the definition of product which we have studied in our previous session. So let us recall that definition. Definition of product, in fact. So let C be a category. Then the product we denoted it by A cross B. Then product A cross B of two objects A and B of C, A and B of category C, is an object of the category C such that we have two conditions. Number one, A cross B is equipped with two maps map from A cross B to A, we denote it by P1 called first projection, and map from A cross B to B, we denote it by P2. This is the second projection. These are called projections. And the second condition is such that for any diagram C to A and then C to B, let's call this map as phi and this map as psi, such that for any diagram in the category C, there exists a unique map from object C to object A cross B, such that the following diagram commutes. And this is the diagram. We have two maps from A cross B, projection 1 and projection 2. And if we have an object C and maps from C to A and C to B, we have named these maps as phi and psi. Then there is a unique map from C to A cross B, let's call it F, such that this diagram commute, which means that is F circle P1 circle F is equal to phi, such that P1 circle F is equal to phi and P2 circle F is equal to psi. So if this diagram commutes with this unique map F, there must exist a unique map F from C to A cross B such that this diagram commutes, then we say that A cross B is product of objects A and B. I regard this definition in fact in order to give definition of product of an indexed family of objects in a category C. So let's come to their definition. This is definition of product of an indexed family of objects. So let C be a category. And let AI such that I belongs to I be an indexed family of objects. Of objects of category C in fact. Then the product of this indexed family, then the product of this indexed family first of all, let's see how we denote this product is denoted as this is the symbol which we use. The symbol pi, you very much are aware about this symbol, but we use this symbol for product as well. So I belongs to I, AI. So this is the way we represent product of this indexed family of objects of category C is denoted as this, and is an object of C this product is an object of category C such that these are the conditions. We have similarly two conditions. First of all, this object or product of indexed family is equipped with maps Remember that previously we have discussed product of two objects. So there were two maps. In this case we are going to discuss product of an indexed family of objects. So for each index I there will be a map. So with maps, these maps will be in the category C, and these maps will be from this product object to each component AI for each I belonging to I. So for each AI there will be a map. We denote this map by PI. These maps are again called projections. And the second condition is existence of a map F, as we have discussed in the case of product of two objects. So if C from C to AI, phi I, for I belonging to I, are diagrams or maps or diagrams in the category C, then there exists unique map from C to this product object let's call it F, such that the following diagram commutes. Now this is the diagram. This is our product object, and from this product object there is projection to each component PI. So for each I there is projection from this product object to AI, and if there is an object C such that for each I there is a morphism, there is a map from C to AI for each I, let's call it phi I, then there is a unique map from C into, then there must exist a unique map from C into this product object, we denote it by F, such that PI circle F, composition of these two, PI composed with F is equal to phi I, and this is for each I belonging to I. This definition seems slightly complicated, but if you pay little attention you can understand it very easily with the help of the concept of product of two objects. For the time being we defer this concept and we will discuss the concept of coproduct. So we come to the concept of coproduct. This is in fact the concept we have to discuss today. In order to understand this concept, let us discuss construction of co-product of two objects in the category of sets and functions. So let us discuss. The construction of co-product of two sets in the category of sets and functions. We denoted this category by SET with capital letters. So let's discuss construction of co-product of two sets in the category of sets. To discuss this construction, first let's see what disjoint union of two sets is. So let me explain it with the help of an example. Disjoint union of two sets. We can have more than two sets, but disjoint union of two sets. Let's take an example. Let set A be 1, 2, 3, 4, 5, 6. And let B set B 5, 6, 7, 8, 9, 10. Let's stop here. So consider these two sets, then their disjoint union. Then the disjoint union is given by note that this is the way we represent disjoint union. A union B. It is slightly different from our standard notation of union, but it is almost same. So disjoint union of these two sets A and B is denoted by this symbol, and this is given by 1, 2, 3, 4, 5, 6. And then 6, 7, 8, 9, 10. You might be little surprised because in this representation we have 5 is repeated and 6 is repeated. Sorry, I should have written here 5. 1, 2, 3, 4, 5, 6. I am making a mistake. Sorry, please forgive me for that. I have written this in wrong manner. Let me do it again. It will help us understanding in fact. So disjoint union of A and B is represented by this symbol A union B, and this is equal to 1, 2, 3, 4, 5, 6. So these are the elements of set A, and then we come to set B 5, 6, 7, 8, 9 and 10. And now let me continue with the sentence I was going to say before. You might be little surprised to see that in this set we have 5 written 2 times and 6 written 2 times. And you know that from your intermediate courses that this is violation of representation of a set. So what we in fact will do is that this 5 is from set A, so we will put A as subscript here, and 6 is again from set A, we put A as subscript here. B5 is from set B, this one 5, so we put subscript B here, and 6 is again from set B, so we put subscript B here. Now there is no violation of representation of a set. This set is 1, 2, 3, 4, 5 from the set A, 6 from the set A, 5 from the set B, 6 from the set B, and then 7, 8, 9, 10. Now 5 subscript A and 5 subscript B are two different elements. 6 subscript A and 6 subscript B are two different elements, and this set is well defined now. This set is called disjoint union of sets A and B. So having done that, note that we can define functions these functions are called inclusions. And these are very simple functions. You already know these functions. So from set A to disjoint union of these two sets, A union B, we have a function, we denote it by I1, injection 1, and you can easily see that this function takes this element 1 of A to this element 1 of this disjoint union. So 1 goes to 1, 2 goes to 2, 3 goes to 3, and so on. And similarly we have injection from B let's denote it by I2. So what this function is going to do is that it will take 5 to this 5 with subscript B. It will take 6 to this 6 with subscript B, and this will take 7 to 7, 7 to 7, and so on. So these are the functions which are just inclusions. 1 goes to 1, 2 goes to 2, 3 goes to 3, 5 goes to 5, 5 with subscript B, 6 goes to 6, 6 with subscript 6, 6 goes to 6, 5 goes to 5, 6 goes to 6, 7 goes to 7. So these are the functions which we can define from sets A and B to disjoint union of sets A and B. So let me remark that is I1 and I2 are just inclusion functions. These are just inclusion functions. And it's very easy to see that these are one-to-one functions, and these are called injections. Evidently I1 and I2 are one-to-one functions. It's very important to note that are one-to-one functions. The functions I1, I2 are called injections. We have already noted that thing, that these functions are called injections. If not, we have written inclusions. Anyway, these functions are called injections. These functions are called injections. In case of product, we also had two functions. When we discussed product of two objects, there were two functions. Those functions were called projections. And in case of coproduct, we again have two functions if we discuss product of co-product of two objects, and these functions are called injections. So in case of product of two objects, the functions are called projections, and in case of co-product of two objects, the functions are called injections. I'm just emphasizing these things. Now, so the co-product equipped with these two functions give us following diagrams. So we have following diagram. So we have co-product of two sets, that is disjoint union of these two sets, A union B, and then we have a function from A to this disjoint union and a function from B to this disjoint union. This function is I1 and this function is I2. So this is the diagram we obtain in the category of sets. Let me emphasize that where I1 and I2 are defined as effect of I1 on any element of set A, on any element X of set A will be equal to X, and effect of I2 on any element Y of set B will be equal to Y. These are inclusion functions. So as we have discussed in our previous discussion, 1 goes to 1, 2 goes to 2, 3 goes to 3, 5 goes to 5, 6 goes to 6, 7 goes to 7. So these are inclusion functions. So effect of I1 on an element X of A is X, and effect of I2 on an element Y of set B is equal to Y. So these are just inclusion functions. Now suppose we have a diagram in the category of sets and functions. And this diagram is similar diagram like this diagram, that there is a set C, and from set C there are into the set C there are two functions from set A and the other function from set B. Let's call this function is J1 and this function is J2. What we are saying is that if there is a similar diagram in the category of sets, similar diagram, in this case functions are coming from A and B to this disjoint union. If there is a diagram that functions are coming from A and B to some other set, maybe the same set but anyway are coming to the set C, this diagram is in the category of sets. So combining these two diagrams, we obtain, now this is our first diagram, that is disjoint union of these two sets is equipped with two functions called injections from A to this disjoint union, then from B to this disjoint union. This is I2. And if we have a set C and similarly two functions to the set C from A and B, J1 and J2. These are two functions from A and B to this disjoint union. And if there is a set C and functions from A and B to this set C, then this disjoint union has a very special property, and let me discuss that property. That is, now we can define a function from disjoint union to the set C, from this disjoint union to the set C, and let's call this function, let's call it G. So then we can define a function from disjoint union to C such that now let me draw this diagram again. This is disjoint union of A and B, and these are functions from A to this disjoint union and from B to this disjoint union. And this is a set C, in fact this one, and functions from A to C, J1, and a function from B to C, that is J2. Now we can define a function from this disjoint union to C. We have denoted it by G, such that this particular diagram commutes. And you understand what does this mean? This means that G composed with I1, G composed with I1 is equal to J1, and G composed with I2 is equal to J2. So let's see what that function is. To see what the function G is, to see what the function G is, we take an element of this disjoint union and see the effect of G on that particular element. Let X belongs to this disjoint union, A disjoint union B. Let X be an element of this particular set. So if X belongs to this disjoint union, then either X belongs to A or X belongs to B. This is the, in fact, defining property of union of two sets. Then either X belongs to A or X belongs to B. And this is exclusively because A union B in our case is disjoint union. So exclusively because this particular set is, it is not just union, this is disjoint union, is disjoint union. So let X belongs to A union B, then either X belongs to A or X belongs to B. Now if X belongs to A, then we define, now note that we have to define G. This is the function we have to define. So then we define effect of G on X is equal to effect of J1 on X. Remember that J1 is a function with domain A and codomain C and 6, and since X is element of A, so J1 will have effect on X and you will obtain an element of C. So effect of G on X, X being element of this disjoint union, which is element of A as well. So effect of G on that element X will be equal to effect of J1 on that particular element X. So this is the way we define this function G. Gx is equal to J1x. And if X belongs to B, then we define effect of G on X will be equal to J2X. Exactly the way we have done above. So this is the way we define G on elements of disjoint union A union B. And Now we have to see this particular thing. So let's see how does this work and how does this work. And G composed with I1, its effect on X will be equal to effect of G on I1X, and this will be equal to, we know that I1X is equal to X. This is the way we have defined I1 inclusion functions, I2 inclusion functions. So I1X is equal to X, so it will be Gx, and Gx is equal to J1X. This is the way we have defined exactly. Gx is equal to J1X. This is equal to J1X. And similarly, G composed with I2, its effect on some element Y of disjoint union will be equal to effect of G on I2Y, and this will be equal to G of Y, because effect of I2 on any element is the same element. So I2Y is equal to Y. And Gy is equal to, Gx is equal to J2X. So Gy will be equal to J2Y. So this is equal to J2Y. So that now note that effect of G composed with I1 on X is equal to J1X, and effect of G composed with I2 on Y is equal to J2Y. So therefore G circle I1, G composed with I1 is equal to J1, and G composed with I2 is equal to J2. And therefore we have proved that this diagram commutes. Therefore the diagram commutes. So let's call this diagram 1, and let's write it as 2. So therefore the diagram 1 commutes. So let me show you again. This is the diagram we have proved is commutative diagram. That is, composition of G with I1 is equal to J2, and composition of G with I2 is equal to J2. So this diagram commutes. We have proved that. So having done that, let's come to one more thing, and that is this particular function we have defined, this particular function G, which we have defined as Gx is equal to J1x if x belongs to A, and Gx is equal to J2x if x belongs to B. This particular function which makes this diagram commutative, this function is unique. Now we come to uniqueness of G. Uniqueness is very important concept in category theory. You must be remembering that when we discussed products, we discussed uniqueness as well there. So let's see that G is unique. So for uniqueness, you already know that what we are going to do is we are going to take an other function from this disjoint union to C, which makes this diagram commute, and we will prove that that function is exactly equal to the function G. This will make G unique. So suppose that there is a function suppose that there is a function from this disjoint union A union B to this set C, and let's call this function H, such that in fact what we are going to do is we are going to draw the same diagram. Instead of G we are going to write H, and if we say that with H this diagram also commutes, then H will become equal to G and G will become unique. So this is what we are going to do. So such that this diagram commutes, which is disjoint union of A and B, and injections from A to this disjoint union, and injection from B to this disjoint union, I1 and I2. And we have C, and similarly we have functions from A to C. We denoted this function by J1, and function from B to C, we denoted this function by J2. And we have suppose there is a function from this disjoint union to C. So let this function be H from A union B to C, such that this diagram commutes. And by saying that this diagram commutes, we mean that composition of H with I1, this composition of H with I1 is equal to J1, and composition of H with I2, this composition is equal to J2. Now let's take an element X of A. Then for X belonging to A, effect of this composition H circle I1 on X will be equal to J1X. H circle I1 is equal to J1. Therefore, effect of H circle I1 on X will be equal to effect of J1 on X, because we have assumed that this diagonal commutes. So because of this, and therefore effect of H on I1X is equal to J1X, and therefore effect of H I1X is equal to X, we have noted it already. Therefore Hx is equal to J1X. and we know that J1X is equal to Gx. J1X is equal to Gx, and this is equal to Gx. So Hx is equal to Gx. Similarly, for y belonging to B, in fact what we are doing is that since this is a disjoint union of A and B, so if we take an element of this disjoint union, that element is either going to belong to A or it is going to belong to B. So first we have discussed, if x belongs to A, then Hx is equal to Gx. Now if we take an element of this disjoint union which comes from B for y belong to B, so for y belong to B, Hy is equal to, we can prove that Hy is equal to Gy. Let me write here. When we say that for x belonging to A, in this case x belongs to disjoint union A union B, because every element of disjoint union is either element of A or element of B. So if it is an element of A, it is from this disjoint union. Anyway, so Hx is equal to Gx and Hy is equal to Gy. So whether x is element of A or y is element of B, effect of H on x is equal to effect of G on x, and effect of H on y is equal to effect of G on y, and therefore H and G have same effect. H is equal to G, and therefore G is unique. Therefore G is unique. So having completed this construction, let's sum up what we were doing. So summing up our discussion, so let's sum up the discussion. So given sets A and B, this is what we have done in fact. So given sets A and B, there is a set, we denote it by this particular symbol, and we know that this is disjoint union of A and B. So there is a set, this particular set, which is disjoint union. So given sets A and B, there is a set, disjoint union of A and B. This particular set is equipped with functions I1, which is injection, and I2, which is again injection. These are called injections. And these functions are such that given in the following diagram. So we draw the diagram with these injections I1 and I2. So this is disjoint union of A and B, and we have I1 from set A to the disjoint union and I2 from the set B to the disjoint union, I1 and I2, such that, this is the important thing, such that for any diagram C and functions from A to C, we called it J1, and function from B to C, we called it J2. What we are saying is that if there is a similar diagram in the category of sets, replacing this particular object by set C, A is there, B is there, these two functions are with different names. So if there is a similar diagram in the category of sets, in the category of sets, we denoted it by capital S, capital E, capital D, then this is what we have proved, then there exists a unique function. We have established that there exists a unique function from this disjoint union to C, such that this diagram which I am going to draw commutes. So you know what that diagram is. This is disjoint union, these are injections, and if there is a set C having functions from A into C and from B to C, then there is a unique function. We denoted this function by G. This is from disjoint union to C, such that this diagram commutes. That is, by commutativity of this diagram, we mean that composition of G with I1, G composed with I1 is equal to J1, and G composed with I2 is equal to J2. So this is the construction we have discussed. We have summed up this discussion with this particular construction, with this particular properties. We say that this disjoint union is co-product of sets A and B in the category of sets. So let's note this particular thing. So let's write it as a note. So we say that this A union B, disjoint union of A and B, disjoint union of A and B. So this disjoint union of A and B is co-product of A and B in the category of sets and functions, which we denote by capital S, capital E, capital T, set. And let's have another note to express that this disjoint union A union B is co-product in the category set. We usually mention the injections along with the injections I1 and I2 as well, and say that disjoint union of A and B, and then these injections I1 and I2, and we say that this particular diagram is co-product diagram in the category of sets, is co-product. In fact, it is sufficient to say co-product, but sometimes we use the word diagram as well. So is co-product diagram in the category of sets and functions. This is the way we write it. So co-product in the category of sets and functions is just the disjoint union of those two objects for which we are discussing the co-product. So co-product of two sets in the category set is just the disjoint union. Now let me recall the definition of product and the definition of co-product in the category set. Product in set, in fact product of two sets in set. So if A and B are sets, then their product is their Cartesian product, A cross B, and this is equipped with two functions from A cross B to A and from A cross B to B. We call projections, projection 1, projection 2. So that if there is a diagram, or if there is a set C and we have two functions from C to A and from C to B, we denoted these two functions by phi and psi. Then there is a unique map from C to A cross B. We denoted it by F. there is a unique map from C to A cross B such that this diagram commutes. Let me write what does that mean. That is P1 circle F is equal to phi and P2 circle F is equal to psi. P1 circle F is equal to phi and P2 circle F is equal to psi. So this is the diagram which explains the construction of product in the category of sets. Now let's see what is construction of co-product which we have just completed. So co-product in set, co-product of two sets in fact. So co-product of two sets is denoted by A union B. This is in fact disjoint union of A and B, and this is equipped with two functions called injections. From A to A union B we denote it by I1, and then from B to A union B we denote it by I2, such that if there is a set C and functions from A to C, we call this function J1, and then from B to C we call it function J2. Then there is a unique map from this disjoint union to C. We denoted it by G, such that composition of G with I1 is equal to J1, and composition of G with I2 is equal to J2. So this is construction of product in the category set, and this is the function of co-product in the category of set. If you see these two diagrams simultaneously, you can very easily make a connection between them. Note that A cross B is product, and P1 and P2 are functions from the product to A and B. A union B is co-product, and I1 and I2 are functions to the co-product from A and B too. In case of product, functions are from the product. In case of co-product, functions are to the co-product. So this is very important thing to note, and other things and uniqueness you can very easily understand. So very important to compare these two diagrams in order to understand difference between concept of product and concept of co-product. Just note the direction of arrows. Arrows are going outside from the product. In case of co-product, arrows are coming into the co-product. So that is the important thing. In case of this unique function is coming into the product. In this case, this unique function is going from the product. So just the reverse to each other. So having done that, now we can have formal definition of co-product in a category of C. So let's have the formal definition. So let C be a category and A and B be objects of C. Let C be a category. Just remember that this is C. I simply put little curve on the top just to make it different from the letter C of alphabet. Sometimes it starts looking like E, but if you draw this C with care, you can do better than me, in fact. So let C be a category. Let A and B be objects of this category C. It is better. Then an object now in case of sets, this is the way we denote the co-product by using this symbol of union. But in a general category, we can use this symbol as well, but the custom is instead of union, we denote the symbol of addition. So then an object A plus B. Remember that this A plus B plus does not mean that plus of you have learned about in your primary school education. This is just a symbol. We are using this symbol instead of disjoint union. So let A and B be objects, then an object A plus, let's call it plus, A plus B is co-product of A and B in the category C if, as in the case of product, we have two conditions in case of co-product as well. So first of all, this co-product which we denoted by A plus B is equipped with maps when we are working in the category of sets, we say functions. But when we are working in a general category, we say morphisms or arrows or maps. Maps is perhaps the simplest word. So we say that if A plus B is equipped with maps from A to A plus B. This is injection 1, I1, and map from B to A plus B. This is I2, injection 2. These are exactly the same maps as we already know. These are the maps. We are writing A plus B instead of A union B. So equipped equipped with maps from A to A plus B and from B to A plus B, which are called injections. In case of product, these were such maps were projections, not exactly such. The maps we used in case of product were called projections. In case of co-product, these are called injections. And secondly, such that for any diagram C is an object and there are maps from A to C and from B to C. We call these maps J1 and J2. So if there is such diagram in the category C, then there exists a unique map. Uniqueness is very important. There exists a unique map from A plus B to C. Let me recall. There exists a unique map from disjoint union to C. So from A plus B to C in the category C, such that the following diagram commutes. And you are very much familiar with this diagram. What we are going to do, you can see it very easily. And this is the diagram. This is co-product. These are injections. And then this is another diagram in the category C, and we have maps from A to C, we called it J1. Map from B to C, we called it J2. Then there must exist a unique map from co-product to C.